Welcome to Pioneer's Knowledge Hub.
What would happen if you fell into a black hole? Falling into a black hole is a fascinating and complex concept, involving some of the most extreme conditions in the universe. According to our current understanding of physics, including Einstein's theory of general relativity, here's what would likely happen if you were to fall into a black hole. As you approach a black hole, the gravitational forces become incredibly strong. These forces would cause a phenomenon known as spaghettification. The difference in gravitational pull between your head and feet would stretch your body into a long, thin shape, resembling spaghetti. This stretching would continue until the tidal forces become too strong for your body's structural integrity, ultimately leading to your body being torn apart. If you were to take a step into a black hole, your body would most closely resemble toothpaste being extruded out of the tube, said Charles Liu, an astrophysicist who works at the American Museum of Natural History's Hayden Planetarium. The event horizon is the boundary around a black hole beyond which nothing, not even light, can escape due to the immense gravitational pull. Once you cross the event horizon, there is no turning back. At this point, the force of gravity becomes so overwhelming that escape is impossible, and you would be inexorably pulled toward the singularity at the center of the black hole. The singularity is a point of infinite density and zero volume at the heart of a black hole. It's where all the mass of the collapsed star is concentrated. As you continue to fall toward the singularity, the gravitational forces increase dramatically. In theory, these forces would stretch and compress your body further until you become part of the singularity itself. As you approach the event horizon, the effects of time dilation become pronounced. Time would appear to slow down for an observer outside the black hole. So while you might experience your fall in a relatively short time, an observer watching from a distance would see it happening over an extended period. This phenomenon is a consequence of Einstein's theory of relativity. The extreme gravitational forces near a black hole cause a profound curvature of spacetime. This curvature is what leads to the bizarre effects like time dilation and the inescapability of the event horizon. The closer you get to the black hole, the more pronounced these effects become. The concept of Hawking radiation, proposed by physicist Stephen Hawking, suggests that black holes are not completely black and can emit a type of radiation due to quantum effects near the event horizon. This radiation is thought to be a result of the interplay between quantum mechanics and general relativity. Over an incredibly long timescale, black holes could lose mass through this process, eventually leading to their evaporation. This idea challenges the traditional notion that black holes are completely black and unchanging. One of the most perplexing questions related to black holes is the information paradox. According to our current understanding of quantum mechanics, information cannot be lost. However, when matter falls into a black hole and is ultimately thought to be compressed into the singularity, it seems to violate this principle. The ongoing debate and research around this paradox highlight the complexities of merging quantum mechanics and general relativity. The behavior of matter and space near a black hole's singularity is where the limits of our current understanding of physics are most evident. The conditions near the singularity become so extreme that the laws of physics as we currently know them break down. This is where the quest for a theory of quantum gravity, a theory that unifies quantum mechanics and general relativity, becomes crucial. Such a theory could help explain the nature of singularities and what truly happens inside a black hole. Despite the wealth of theoretical ideas and mathematical models, observing the interior of a black hole is exceptionally challenging due to the event horizon's impenetrable nature. However, advancements in astronomical observations, such as the Event Horizon Telescope's groundbreaking image of the black hole in the galaxy M87, provide us with indirect insights into the effects of extreme gravity and the behavior of matter around black holes. From an observer's perspective, the experience of falling into a black hole would depend on their trajectory and position relative to the black hole's rotation and curvature of spacetime. This leads to interesting thought experiments where two observers falling into a black hole could have very different experiences, with one potentially experiencing a more rapid or slower journey toward the singularity compared to the other. Some theories propose that black holes might be connected to other regions of spacetime through exotic structures called wormholes. If such wormholes exist and could be stabilized, there might be a possibility of exiting a black hole through a connected wormhole. However, This idea is highly speculative and faces significant theoretical challenges, including the stability of wormholes and the need for exotic matter with negative energy density. The Firewall Paradox is a controversial idea that arises from trying to reconcile the principles of quantum mechanics with the behavior of matter near a black hole's event horizon. According to some interpretations, matter falling into a black hole might become a firewall of high-energy particles at the event horizon, violating our understanding of smooth transitions in spacetime. This concept challenges our understanding of how black holes interact with quantum mechanics. The idea of Hawking radiation brings up a perplexing question. If black holes can emit radiation and eventually evaporate, what happens to the information of the matter that fell into the black hole? The current understanding suggests that information cannot be lost, but the process of Hawking radiation seems to involve a loss of information. Resolving this paradox is a significant challenge in the study of black holes and quantum mechanics. The study of binary black hole systems and their mergers has gained immense importance due to the detection of gravitational waves by observatories like LIGO and Virgo. These observations provide valuable data about the behavior of matter and spacetime near black holes, confirming predictions made by general relativity. Black hole mergers also offer insights into the masses and spins of the black holes involved. First of all, you approach the speed of light as you fall into the black hole. So the faster you move through space, the slower you move through time. Furthermore, as you fall, there are things that have been falling in front of you that have experienced an even greater time dilation than you have. So if you're able to look forward toward the black hole, you see every object that has fallen into it in the past. And then if you look backwards, you'll be able to see everything that will ever fall into the black hole behind you. In summary, black holes remain some of the most enigmatic and intriguing objects in the universe. While our understanding of their behavior and properties has advanced significantly, there are still many unanswered questions, and the study of black holes continues to push the boundaries of our knowledge in both theoretical and observational realms. As we explore the cosmos and develop new technologies, we may uncover even more about these cosmic giants and their profound influence on the fabric of spacetime. So the upshot is, you'll get to see the entire history of that spot in the universe simultaneously, from the Big Bang all the way into the distant future. Not such a bad way to go, in the grand scheme of things. What do you say? Please do like, share and subscribe to my channel. Thanks for watching.